Section 16.8, Stokes theorem. The Stokes theorem is a high-dimensional version of the Corinth theorem you studied earlier. Let's recall the Corinth theorem. C is a positively oriented simple closed curve in the plane, and D is the region bounded by the curve. The vector field is a two-dimensional vector field and has continuously partial derivatives. Then the line integral along the curve, closed curve, that is another form of the line integral, can be evaluated using this regional integral. Q sub x minus P sub y is the integrand along the region, and it can be written in this vector form. Regional integral and curl of f and is a normal component. Okay, that is the Corinth theorem you learned earlier. Let's see here the Stokes theorem. S is an oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth curve C with a positive orientation. Now, in Corinth theorem, the surface is on the plane. Now, in Stokes theorem, surface is a general surface in three-dimensional space, and we consider the boundary of the surface. Now, F is a three-dimensional vector field, and have each component has continuous partial derivatives. Then the line integral and along the curve of the vector field can be obtained through that one. So here's the curl along the surface, and we try to get integral through this the surface element. Okay. In definition, this notation means that for surface integral, because we are dealing with, for instance, the flux, so that we have to consider only normal components. The tangential components has no meaning. So here, in definition, for this surface integral of vector fields, we are considering only the normal component. And now by using known identity for normal vector and ds, we can reach at this formula. So we'll use that formula for evaluations. Okay, and this one for Corinth theorem is a special case of this Stokes theorem. And this one is a general normal component to the surface. And of course, K is the normal component of plane surface. So Corinth theorem is the special case. Okay, let's try to solve a problem. Evaluation of line integrals. Evaluate this line integral when f is given in this way and C is the curve of intersection of the plane and cylinder. Okay, let's try to visualize the surface. Okay, these are coordinates, x direction, y direction, that is z direction. The cylinder of radius 1 is given in this way. And now there's plane, it's cut by that plane. That is 45 45-degree angle in YZ plane, and in X direction the same, so that the plane will cut the cylinder in this way, so that the surface S is given in this way. That is now S. Okay. Okay. For this problem, we'll use this formula, and along that is positive oriented, so the C must be running this way. And now Stokes theorem says that one, but practically we'll use this formula to evaluate the integral. So we have to find curl of f, okay, and also we have to find that one. Okay, that is determinant. We are using that standard formula. There's I, J, K, and that operator vector is x derivative, y derivative, and z derivative. Now the vector field here is minus y squared, and second one is x, last one is z squared. So from here, for I, the minor is this portion. Derivative will be 0, derivative will be 0. Okay. And how about for j? Now minus 1, 2, 3, 4, these 4 elements. And we apply this first, 0, now again 0. Okay. Now for k, the minus this 4, x derivative is 1. Now y derivative is minus 2y, so along with one more minus, so 1 plus 2y. Okay, we got the curl of f, and we have to now parameterize the, we have to find that one, but already for that one, okay, we have now z equal to minus y, right? The plane itself can be parameterized in this way. Of course, here the r, along with this one, r must be now x and y, and 2 minus y, right? Okay. And of course, here now x and y must be inside the cylinder, so that that one must be x squared plus y squared is bounded by 1, right? So that is the, for that one, it's a special case, so that r sub x cross r sub y must be, okay, from here, minus g sub x, which is 0, minus g sub y, which is 1, and the final is always 1. So we try to get dot product, r sub x close r sub y. That one is okay, 0, 0, and 1 plus 2y, right? So we got the integrand. So here, the given integral is the same as now double integral over d, and 1 plus 2y dA. D is a polar region, whole circulation, so angle must be from 0 to 2 pi. R, radius 1, from 0 to 1, and that is 1 plus 2 y is r sine theta, and we have another r, scaling factor for polar coordinates, and dr d theta. Now we consider separately the integration. If we consider this second one, then it is separable in sine integration. Theta is moving from 0 to 2 pi, so that one, for this part, here halfly positive and halfly negative. So the contribution must be 0. So we ignore this portion. So remainder part is only R, right? So it's the same as integral from 0 to 2 pi for the angle, for radius from 0 to 1, and then we have only R, dr, d theta. For theta integration, we have 2 pi. For R integration, half R squared from 0 to 1, so that it'll be half. So we have the final answer, pi, right? Okay. Here, we'll see one strategy. Surface integral and line integral can be obtained in this way. Through the Stokes theorem, we know the surface integral of the curved vector field is the same as the line integral over the closed curve, the boundary of the vector field. It is known from Stokes theorem. In evaluation, we are using these evaluation formulas. So practically, after parameterization, you have to get this quantity and or this quantity. Your problem is asking either evaluation of that one, then you may use the other part. If the problem is asking evaluating this part, then you can use the other part. Either way, you can do that. For this side, you have to find a transform from a region D, and now in a function of two variables, u and v. And for that one, you have to find a and b. Okay, that must be comma. And a to b and r of t. So you can use the other one to evaluate one of them. Okay, let's see this problem. Use Stokes theorem to evaluate the surface of integral. Surface integral, okay, it is asking evaluation this one using Stokes theorem, which means that you can use the other part to evaluate the given one. Now, f is given in this way. S is the part of sphere of radius 2 that lies inside the cylinder of radius 1 and above the xy plane. There's two parts, so that we are considering only a proportion. Okay, let's try to visualize the surface. This is the rectangular coordinates x, y, z. Okay, radius to surface. Okay, let's try to make surface the sphere. That is radius 2, like that. And inside the cylinder of radius 1, in a vertical cylinder, consider this vertical cylinder, and that is, now there is radius 1, and inside, so that must be this portion. Okay, there is now S, and C will be curved like that. Okay, we focus on only this portion. We have to get the surface integral of curve F, and using now line integral along this boundary. Okay, if you want to get that one, then you have to get parameterization. This one, if we focus on this curve, then now this is a flat circle, and we have to find the height. How? From these two equations. The intersection is made from now x squared plus y squared plus z squared equal 4. One equation is this one. Another equation is Now x squared plus y squared is 1. This is a sphere, this is a cylinder. From there on, okay, this portion is 1, which means that z squared equal 4 minus 1. So we have a 3. That means z equal plus minus square root of 3, but we are considering only upper portion. So that is square root of 3. And flat curve, so we can get here r of t, one whole circle, that is cosine t in x direction, in y direction sine t, and height is square root of 3. Right? Now, of course, t must be from 0 to 2 pi, whole circulation. Okay, so now we have to get fr dot r prime. Okay, along with that representation, we can get now f of r. First component is x times z, x and z, square root of 3 cosine t. Second one is yz, y is a sine t, and z is square root of 3. Okay, we'll write here square root of 3. And final one is xy, that is cosine t and sine t product. Now, what is r prime? R prime is minus sine t. Second one is cosine t. And final one is 0. The square root of 3 becomes 0. Okay, so we have from here, the product is square root of 3. Okay, that's minus. And cosine t and sine t. And second one, okay, that is plus square root of 3 cosine t, again sine t. Last one, this product is 0. Okay, one is negative, one is positive, so that we have 0. Okay, in this integral, the integrand becomes 0, so that the given integral is from 0 to 2 pi, and that is 0 dt, so it must be 0. That is the final answer. Okay, again, when you see the problem in asking the Griffith theorem, then that is the right strategy. You have to use this theorem, but practically in evaluation, you have to either this one or that one to get the asked integral. And first step is to recognize the curve or surface or region, and then you have to introduce a transformation, so that using the formula, evaluation formulas, you can get the integral the problem is asking. Okay? Okay, we solved this problem in the classroom, and through the Stokes theorem, either this one or that one. Now, if we consider, right now there is a surface integral. However, Stokes theorem is saying that it's the same as a line integral over the boundary. So these are the same. Two surfaces have the same boundary, so that line integral must be the same. So that is the answer. For the remainder problem, I believe you can figure out. Okay, thank you.